Hello, everyone. Welcome back to the second episode of Computer Architecture. My name is Aritrash, and this is the second episode that I have been continuing since the last time I uploaded this or lectures on computer architecture. So, last day we saw what's a computer. We looked at basic definitions, principles, and uses. We saw how a computer is a big calculator, computing generations, about Moore's law. One thing that I forgot to do last episode was that I said George Moore. I'm sorry, that would be Gordon Moore. So that's my bad. So yeah, that's that. So today we're going to start with semiconductor physics and transistors. We're going to talk about the physical, chemical, and mathematical properties of semiconductors and how they work and how do they actually take a part in computer engineering. So here we go. So let's talk about material sciences in computing. In order to know about computers, one must be acquainted with the laws of physics, exceptions in chemistry, and functions of mathematics. Everybody loves this. Computers work using semiconductor physics and quantum mechanics. We'll get into them as we learn more about semiconductors. Semiconductor fabrication requires the knowledge of periodic and chemical properties of different materials. Yes, we do use silicon, we also use boron, we use phosphorus, and so many more different materials for doping. And every signal produced by a computer is a mathematical function. Oh, yes, it is. So let's talk about semiconductor physics. The knowledge of semiconductor physics is crucial to understand the working of a computer. Every code that is compiled on a system moves through layers of abstraction. So let me quickly just say that what are the layers of abstraction in a computer? A computer system has various layers of working. We start with the silicon wafer layer, then we go into the microcodes, then we get the instruction set architecture, the ISAs, we get the RISC, we get the CISC, then we have the operating systems. Over that, we have got the application level, then we have the user code, which is the highest level of abstraction. So the final and the lowest physical abstraction layer is semiconductors, or in case of computers, is the silicon. Silicon by its own is not that useful in computing. This is where the knowledge of semiconductor physics is required. As you can see in this image, silicon is the 14th element in the periodic table. It has an atomic weight of approximately 28.08 atomic mass units. Symbol is Si. It has an electronic configuration of neon 3s2 3p2. It's right in the middle of the acid base properties. It's not an acid, not a base. It's right in the middle. It has got a diamond crystal lattice with a solid at physical solid physical state at about 20 degrees Celsius at room temperature. So let's talk about doping. The introduction of other materials or impurities into a pure substance to induce certain physical, chemical, or electrical properties into a substance is known as doping. Silicon can be doped into p-type by doping it with group 13 elements such as boron, and into n-type by doping it with group 15 elements such as phosphorus. P-type and n-type silicon have different properties than intrinsic or undoped silicon. Let's see that where does the n-type and p-type silicon shine. Let's talk about p-type. P-type silicon can be manufactured by doping intrinsic silicon with group 13 elements such as boron. The boron dopant, the one we are doping with, is called the dopant. So the boron dopant has one less electron than silicon in its outer shell, thus creating an electron hole. The hole acts as an electron acceptor, hence create an illusion of a positive charge carrier, hence the name p-type. So it creates a hole which, where electrons can actually take their places, and hence they can carry the charges around. Upon desirable electrical and mechanical characteristics, controlled charge flow can occur. Similarly, we have N-type silicon. N-type silicon can be manufactured by doping intrinsic silicon with group 15 elements such as phosphorus. The phosphorus dopant has one extra electron than silicon in its outer shell. The extra electron is loosely bound and becomes a free charge carrier. Upon desirable electromechanical characteristics, controlled charge flow can occur. One thing I would like to say is that even though there is an extra free electron, the thing is the entire dopant or silicon remains atomic or electrically neutral because all the charges are actually balanced and the electrons are just floating. It's like what we get an electron C on a metal. So let's talk about the p-n junction. When a p-type and n-type silicon are joined together, the junction point is known as a p-n junction. This junction cannot be made by simply welding or tightly packing the pieces together, since the junction must be atomic and physical, or welding joining has microscopic air gas in between them. So when this junction has been made, atomic contact has been made, and when voltage is supplied to this junction, electrons from the n-type move towards the holes of the p-type, thus establishing a current flow. Now we come to the star of the show, the transistors. When an n-type material is atomically joined with a p-n junction with a p-type material, as you can see, uh, it creates an n-p-n junction. Similarly, a p-type material can be used to build a p-n-p junction. So when a small current is supplied to the middle material, that is P in the NPN or N in the PNP, a large current can be made to flow through the ends of the junction. This exact idea is the core of bipolar junction transistors, an electronic switch that can enable or disable the flow of a large current using very small current. So a bipolar junction transistor, sometimes referred to as a BJT or a BPJ, are the most basic form of transistors. These transistors are used all the way from second to some third generation computers, audio equipment, more as switches or amplifiers. There are three terminals: a collector, which collects the high current, a base, which is the terminal that accepts the small switching current, and the emitter, which emits the switched current. One can simply think of the collector as input and the emitter as output for the high current. Now we come to the more modern type of transistors, which are the field effect transistors. A field effect transistor is a type of transistor that doesn't use three different materials for having the two junctions, rather two materials having one junction, making it unipolar. Unlike BJTs, which are current control devices, that's the base current, FETs or field effect transistors are voltage control devices. They are controlled by the gate voltage. Current causes resistive losses in forms of heat. We all know about the copper losses, the I square R losses, which cause the BJTs to be more power consuming. FETs are hence more power efficient in switching. Now let's talk about MOSFETs. In order to make the input impedance higher, that is the input resistance higher for logic operations, we only want two single parts, that in binary logic, the 1 and the 0, which translates to electronics as 0 volts or ground voltage and relative higher voltage. A layer of silicon dioxide over the gate is applied. For efficient contact points with silicon, a thin nanometer scale layer is deposited on the oxide layer of the gate. So this creates undoubtedly one of the biggest invention of mankind, the metal oxide semiconductor field effect transistor, the MOSFET. In MOSFETs, the emitter is called the drain, the collector is called the source, whereas the base is actually called the gate, as we can see in the image. Now we talk about the different types of MOSFETs. We start with PMOS, built on an N-type substrate. As we can see, the blue colored is an N-type substrate. With the P-type source and drain regions, you can see the orange ones. A thin oxide layer insulates the gate. You can see the white gate oxide. These are generally slower than NMOS. We will talk about NMOS because electrons, which are the majority carriers in NMOS, move more easily than holes, which are majority in PMOS. A PMOS transistor turns on or conducts voltage when the gate voltage is low, negative relative to the source, and off when the gate is high, positive. So when we provide a 1 to the gate of this PMOS, that's an on or a high, we do not get any kind of conductance. But when we provide a low voltage, that is a 0, we get conductance on the PMOS. Let's talk about NMOS, built on a P-type substrate. You can see on the right, you get the pink color P substrate with N-types source and drain regions. You can see the blue one. A thin oxide layer insulates the gate. Now this turns on when a positive gate voltage, creating an N channel for electron flow, and turns off or blocks with 0 or low voltage. So this is just the inverse of a PMOS. When you provide a 1, it turns on. When you provide a 0, it turns off. This is way much faster than PMOS because electrons move more easily than holes. So let's talk about things to remember. That material sciences play a huge role in understanding computer architecture and computers in general. Silicon chemistry is something one must be well aware of in order to fully grasp the engineering behind modern computing. However complex the algorithm, from neural networks to data analysis, runs only because the transistors operate the way they do. Now, if you like this content, again, I would greatly appreciate if you would drop a like. And if you have anything that I can do, that you want anything from me, newer stuff, if you want, maybe as I told in the first video, if you want to get the software stuff, you can always get it down in the comments. I would really love it. And yeah, thanks. Bye bye.